So let's try and get a little more information about geometric series. I'd like to know a couple of things. First of all, when does a geometric series converge and have a finite sum, and when does it diverge? And related, what is the sum of a given geometric series if it does converge? To figure that out, let's look at the partial sums. The partial sums, remember, are sums of the first n terms, whatever n happens to be, of the series. This is important because, of course, there's no real definition in math of what an infinite sum is, but we know what a finite sum is. The definition of an infinite sum is essentially going to be the limit of the sequence of partial sums. So we have to start with finite sums here. So Sn, recall, is the sum of the first n terms in the series. Now, if I'm talking about the generic geometric series, sum as n goes from 1 to infinity, of a times r to the n minus 1, where a and r are arbitrary real numbers. Let's work out what Sn has to be. So, Sn is the sum of the first n terms. The problem is that depending on what n is, this is going to have different numbers of values in our sum. It's going to start with a plus ar plus ar squared plus, and so on. We'll keep going, plus eventually the last thing that we'll add here will be the nth term, and that is a times r to the n minus 1. The trouble here is that this is not what we call a closed form formula. It's not easy for me to just plug a number n into here and see what I get, because the trouble is if I want to figure out what the 100th partial sum is, I'm going to have to add up 100 terms. If I want to know what the millionth partial sum is, I'll have to add up 1,000,000 terms. The further down you want to go, the bigger partial sum you want, the more work you'll have to do, and there's no limit to how much you have to do. I want a formula for Sn that is equally simple no matter how big my n is. I don't care if I have to make 100 calculations as long as I only have to make 100 calculations no matter how big n gets. I want a closed form formula that doesn't involve some kind of rapidly growing sum. How can we figure that out? Well, there's a good strategy that'll work here, and the strategy is to start by taking this equation we just wrote out here and multiplying it by r. So let's try that. So r times Sn, what's that going to be? Well, it's going to be r times each of the terms in this sum. So r times a is ar. Now, I could write that right here, ar, but I don't want to. I want to write ar lined up with the previous ar. Now, r times the next term, which was r times that is going to be ar squared. Now, r times the next term, that was ar squared, now we're going to multiply by r, that's going to become ar cubed. Of course, there is, hidden in these ellipses here, there's already an ar cubed and so on. All the terms that we didn't write out are still here, we just didn't write them out. What is the last term going to be? Well, the last thing we're going to get, let's see. The last thing is going to be what we get if we multiply ar to the n minus 1 by r. That means we're going to multiply an additional r in here, which means we're going to raise the power on the r by 1. And we're going to get ar to the n. Well, now what? Let's try subtracting the second equation from the first. Let's take this entire second line and subtract it from the first line. So on the left-hand side, I'm going to have Sn minus Rsn. On the right side, what will I get? Well, there's this a right here, so I'll have an a here. Now, we're going to have ar minus ar. So what do I get? Just 0, nothing, right? So plus 0. We're going to have ar squared minus ar squared. That's going to be plus 0 again. There is an AR cubed in here. It's just, I just didn't write it out, but it's in the ellipses there. And AR cubed here, they're going to be subtracted, so we get plus 0 again. Plus, etc. Now, AR to the n minus 1, that is again appearing in our second line, sort of missing in here in the ellipses is an AR to the n minus 1. Those are going to cancel out, and we're going to have a 0. But we do have that last term there in the second line, the AR to the n. Now don't forget, we are subtracting the second line. So we are subtracting AR to the n. This is really good news because we took two expressions that involve an arbitrarily long sum that might have lots and lots of terms, but by subtracting them, we got rid of most of those terms, and in fact, what we're left with is a closed-form formula on both sides. Sn minus Rsn equals A minus AR to the n. We can work with this. What do we want to solve for? What I want to know is what is Sn. So I'm going to take my left-hand side, and I'm going to factor out Sn. If I do that, it's Sn times 1 minus r. And that equals A minus AR to the n. I could even factor out the a from here if I want to. Maybe I'll do that. A times 1 minus r to the n. Now, if I want to solve for that partial sum, solve for that Sn, I'm going to get Sn equals, I'll just divide by 1 minus r. So I'm going to have A times 1 minus r to the n over 1 minus r. And that is my nth partial sum. This is a closed form formula for the nth partial sum. Now, of course, this only works if we have a geometric series. If we had a different kind of series, this would not work. This works because we're relying on the fact that when you multiply the partial sum by r, that common ratio, you get something that will cancel out most of the terms that were in the original Sn. That's not going to work if your series does not have a common ratio, if your series is not a geometric series. This only works in this one specific case. But we found a formula. Good for us. What can we do with this? Well, I want to know, when does a geometric series converge? And if that series converges, what is its sum? So to figure that out, I need to find out the limit as n goes to infinity of that sequence of partial sums. I want to know what's happening to those partial sums as you add more and more and more terms to them. So let's work that out. Well, we're going to have the limit as n goes to infinity of the expression that we just figured out, which is going to be A times 1 minus r to the n over 1 minus r. Something very important to note here. This is a limit in terms of n. That means that a and r are fixed. They are constants as far as we are concerned. The only thing changing is n. So in fact, perhaps I'll just clean this up a little bit. I'm going to factor out that, limit as n goes to infinity. I'm going to factor out that a over 1 minus r, that is itself just a constant. And I'm only going to worry about 1 minus r to the n. What is happening as n goes to infinity? Well, what does r to the n do? If you imagine, say, 2 to the n as n goes to infinity, you're going to multiply by 2 more and more and more times, and that 2 to the n is going to go off to infinity, and then 1 minus that's going to be negative infinity, but that doesn't matter that much. The important thing is that is not a finite value, right? On the other hand, let's say you had 1/2 to the n as n goes to infinity. Well, you're going to have a half times a half times a half times a half. That's going to get smaller and smaller and smaller. And 1 minus that will be finite because that 1/2 to the n is going to approach 0, and 1 minus that will therefore be 1. In fact, even if the r is negative but very small, multiplying it by itself multiple times is still going to cause that to approach 0. Say your r was negative 1/3. Negative 1/3 times negative 1/3. It's going to fluctuate back and forth, positive, negative, but it's going to get closer and closer and closer to 0 as you go. So if r is between negative 1 and 1, then r to the n is going to go to 0. Because the r is very small, and multiplying it by r more and more times is going to cause us to go to 0. So 1 minus r to the n will go to 1. So the limit as n goes to infinity of a over 1 minus r times 1 minus r to the n is just going to be a over 1 minus r, because it'll be times 1. On the other hand, if r is greater than 1, or if r is less than negative 1, in other words, if r is far from 0, either positive or negative, then multiplying r by itself multiple times is going to cause it to go off to infinity or to fluctuate between positive and negative infinity. Then r to the n is going to diverge. It will go to infinity if r is positive. If r is negative, it's going to be infinitely large, but it fluctuates back and forth, positive, negative, and there is no actual limit. So that means that the limit as n goes to infinity of our partial sums also diverges. So, little side note here. What about r equals 1 or r equals negative 1? My recommendation is that you try these yourself. Those don't quite fit into our little situation here. First of all, if r equals 1, then what is that 1 minus r in the denominator? That's going to go to 0, right? That means we're going to divide by 0. What that means is if r equals 1, this whole formula we came up with for the partial sum doesn't work. But that's okay, because you can plug 1 in for r back in the original formula for the series and look at what series do you actually get if your r is 1. And once you play around with that, you'll see immediately whether that series converges or diverges. What about if r is negative 1? Well, again, try plugging in negative 1 for r in the original formula for the geometric series and write out what the terms of that series look like. And what happens if you start taking partial sums? What is happening to those partial sums if you do that? Again, you'll find it doesn't quite fit into the rest of the scheme here, but it does give you a series that you definitely can tell whether it converges or diverges. It turns out actually in both of those cases the series is going to diverge. Let's put this all together. Here's our theorem. Given a geometric series, the sum as n goes from 1 to infinity of a times r to the n minus 1, if the absolute value of r is less than 1, in other words, if r is between negative 1 and 1, not including those values, the series is guaranteed to converge, meaning it does have a finite sum. And the sum is actually going to be exactly a over 1 minus r, whatever that is. We just proved that. On the other hand, if the absolute value of r is greater than or equal to 1, including 1 or negative 1, then the series diverges. It does not have a finite sum. And now that we know this, we can go back and apply this information to any geometric series that we see without having to go through this whole process over and over and over again. So let's go back and look at the 3 examples of geometric series that we started with. And let's try and apply these. Let's figure out for each series whether that series converges or diverges. And if it does converge, what is the sum? So for this series, the sum as n goes from 1 to infinity of 3 over 2 to the n, we worked out that our r is 1/2. Each term gets multiplied by 1/2 to give you the next term. Our r is 1/2. And our a is always the first term. In fact, that's going to be true whether n starts at 0 or 1 or anything. So that's going to be 3/2. Since our r is 1/2, since the absolute value of 1/2 is in fact less than 1, because it's 1/2, the series converges. This is going to be very important from this point forward. From this point forward, we're doing these problems. We are not just trying to do a computational problem where we spit out a numerical answer at the end. For the problems that we're going to be doing in this chapter, our goal is to prove that a certain thing is true, either to prove that a series converges or to prove that it diverges. So your answer to any of these questions should look like the following form. Because of this fact, or this theorem, in this case, since this is a geometric series where the absolute value of r is less than 1, the series converges by the geometric series theorem. Okay? And because the series converges, we also know what the sum is. The sum is a over 1 minus r, which is 3/2 over 1 minus 1/2. That is 3/2 over 1/2, which is 3. That is the sum of our series. If you want to check this, you could check this by actually computing some partial sums. 3/2 plus 3/4, what is that? Add 3/8 to that, what is that? Add 3/16 to that. You're always going to get a number that is getting closer and closer and closer to 3. But it's always a bit less than 3. But the more terms you add, the closer that result gets to 3, the smaller the gap gets between that partial sum and 3. So you can satisfy yourself that this series does converge to 3 by adding up some of the terms. So there we go. Let's look at the next example. For this example, we worked out that it is a geometric series because there is a common ratio of the terms. We checked that. And that common ratio, that r, turns out to be negative 2/5. And our a, which is our first term, is 10. So our r is negative 2/5. The absolute value of r, therefore, is the absolute value of negative 2/5, which is positive 2/5. Is that less than 1? Yes, of course it is. It's less than 1. So, we can say, since this is a geometric series, and the absolute value of r, which is the absolute value of negative 2/5, is less than 1, the series converges. Okay. And its sum, again, is going to be a over 1 minus r. Now our a here is 10, and 1 minus our r is negative 2/5. So let's work that out. We're going to have 10 over, let's see, 1 minus negative 2/5 is 1 plus 2/5, which is 7/5. So 10 over 7/5 is going to be 50 over 7. So not a very neat and tidy number, but it's a fraction. There we go. That is our sum. Okay, a little over 7. 7 and a 7th, in fact. For our last series, the sum as n goes from 1 to infinity of e to the n over 12. We worked out, again, this is a geometric series. And our r is e, and our a is e over 12. The problem here is that r is e. We know how big e is. E is approximately 2.718. It is exactly, e is approximately 2.718. It is certainly bigger than 1. So, does the series converge or diverge? Well, since the absolute value of r, which is the absolute value of e, which is e, is greater than or equal to 1, the series diverges. And since the series diverges, we cannot find a sum for it. There is no ultimate sum. In fact, if you tried to work out what the sum was using that formula, you'd say a over 1 minus r. Well, your a would be e over 12, and 1 minus r would be 1 minus e. Well, the problem here is 1 minus e is negative, because e is more than 1. This is actually a negative number. If you attempt to use the sum formula for a geometric series that has no sum because it diverges, you can plug numbers into that formula, but the answer will be nonsense, and in fact you'll oftentimes get a negative answer, which clearly doesn't make any sense, because how can we add up a bunch of positive terms and get a negative answer? It's nonsense. There is no sum here. So you shouldn't even attempt to plug the numbers into that formula, because the results don't mean anything. So here's how we can identify a geometric series by identifying whether there is a common ratio r. And once you know what that r is, if it exists at all, you can determine whether that series converges or diverges by looking at whether the absolute value of r is less than 1 or greater than or equal to 1. And if that series does converge, we actually have a formula for the sum. This whole process breaks down if your series is not a geometric series. This example here is not a geometric series. There is no common ratio. The terms are shrinking in this case, but are they shrinking fast enough to actually give us a finite sum? We don't know until we attempt some further strategies, until we have some more tools under our belts to help us solve this problem. We don't know if this series converges or diverges because we cannot use the theorem about geometric series here.